Hi everyone, I'm José Bermejo. I'm at the Instituto de Canarias, but I will be moving to here to Concord in January. And today I'm going to speak about primordial non-Gaussianity, and in particular I will focus on how we improve the measurements on primordial non-Gaussianity with some new non-standard cosmological information that is called Gaussian fluctuations. So I will first briefly introduce the primordial non-Gaussianity topic, then I will show briefly some analysis that we did in the test collaboration of cross-correlating the plan CMB lensing with DSLRs to measure PNG. Then I will introduce a little bit the new cosmological observer that I've been exploring for improving the sensitivity PNG, and then show some applications of this methodology to the data from Wild Research Development. So essentially, we want to measure PNG primordial non-Gaussianity because it encodes key information about inflation. So we know inflation happened and is defined by the potential, and again, this potential, depending on the model, can have some level of non-Gaussianity that is usually parameterized in the literature through definite parameter. Such that if we measure something different from zero, it's just a matter of having non-Gaussian initial conditions. So basically, we have two cosmic windows to measure the PNG. The first one is the CMB light spectrum, which provides currently the tightest measurement of PNG, which is plus minus 5, and compatible with Gaussian initial conditions as measured from the plant data. But then also we can measure PNG from the large-scale structural surveys as to the imprint of the primordial non-Gaussianity in the galaxy bias. In this sense, things are improving with time. We are already below 10 of sensitivity with the LSE TR1 quasars and LRGs, power spectrum in 3D. And essentially what we can do with LSS is just to trace the imprint of FNL in the scale-dependent bias, which is defined by this formula over here. Here in this picture, we can see some simulations of universes for different FNL values, various spring values. So it is obvious that having now very different non-zero FNL has its impact on the structure that we see today. So the most challenging issue when we are measuring FNL from LSS are usually our systematics. So essentially the problem is we have the PNG signature over here in the lower multiples, largest scales, which means these scales are also sensitive to systematics. For example, change on the observational conditions, sometimes also extinction or star density that comes from our own galaxy. And a proper measurement requires to properly mitigate systematics. One other possibility is just to perform cross correlations with other tracers that have different systematics, for example, the CMB lensing. So that is what we did in the DESI collaboration, also to try to understand what is the sensitivity of the CMB cross correlation to primordial non-Gaussianity. So that project was using actually the DESI legacy survey, which was a photometric survey that was carried out before the spectra were actually measured in Arizona, and we were also using the CMB lensing plan. So this project involving these people here, essentially 90% of the work was to understand the impact of observational systematics on the analysis, because cross correlations can drop it, but essentially we also need to perform a good mitigation in order to have a realistic analysis metric that is not affected by the errors on the output spectra. So essentially we were just testing on the pipeline, creating contaminated mocks, then applying a neural net mitigation code developed by someone in DESI, testing if we could recover not the input data. Finally, the results were a sensitivity to FNL close to 20 when we were combining the autocorrelation of photometric LRGs, CLGG, and the CMB lensing cross-correlation with LRGs. These results were out earlier this year. It essentially was one of the best measurements using CMB cross-correlations. But now we are trying to look for new techniques that could boost or improve a little bit this kind of two-dimensional analysis. So essentially, we want to improve things. We can do or just switch to new data or just try to improve a little bit the techniques. So in this sense, I'm trying to push two directions. One is to add more cosmological observables, and I will focus now in one observable that is called angular fluctuations. And the other approach, which is more ambitious, what I would say is multi-tracer approach using many tracers, even many surveys that overlap in redshift have different biases, so we can somehow compare and improve the final sensitivity. So I will now introduce the angular fluctuations observable. So essentially, we do cosmology in two dimensions. We can think about the projective galaxy density as our standard observable. But in this case, what we have is the redshift itself introduced as a field. So ARFs, angular fluctuations, essentially measure the deviations of the average redshift of the sample along the different directions of the scan. This observable was proposed in the literature a few years ago. It is a quantity that is sensitive to the galaxy bias, to the sensitivity to peculiar velocities. So once this is sensitive to the galaxy bias, it will be also sensitive to primordial non-Gaussianity through the scale-dependent bias effect. So ideally, if this observable is so if systematics are redshift independent, this observable should be insensitive to systematics. This is not always true, but this is the theory. So in order to test whether this observable is useful or not for measuring FNL, we have been applying this new methodology to the data from Quaya, which was also produced yesterday in some talks. So Quaya is essentially a quasar catalog that comes from Gaia data and some unwise data too, and it samples to redshift 4 and contains 1.2 million quasars. So it's the largest volume of quasars ever sampled. It was used before to measure FNL using this quasar density and CMB lensing earlier this year, getting an error bar around 22. We are now trying to see how much we can improve this measurement by adding the angular fluctuations in the analysis. The future forecast predict with 30%. We are essentially developing a pipeline which will be improving in the future, but this is the first version of the pipeline. Everything relies on some theory models that include angular fluctuations in a one code. And from that code, we are essentially generating Gaussian simulations, projective simulations to produce covariance matrices, and then we apply the typical measurement of the power spectra to compare the data with the theory. So these are the main results of our project, which are about to be submitted to archive in this month. So essentially, if we adopt a bias evolution model with two free parameters, we were measuring jointly 3 parameters, so FNL and 2 parameters related to the bias evolution. And we get a sensitivity which is around 40 for angular fluctuations. But if we combine everything, if we combine density with angular fluctuations and CMB lensing, we can get down the uncertainty to sigma FNL of 13. And this is so far the second best measurement of FNL from LSS after the year 1 P of K analysis. And it's also the best one actually using projective summary statistics. So since this methodology is kind of promising, we also want to know why was no plan Very first time.
Oh, that's.
Yeah, essentially the idea is to apply this methodology to DESI data and to Euclid data too in the future, since we have been showing that is promising for Goya data. Then also we would like to at some point explore a multi-tracer approach to combine some information from many surveys. And yeah, I think I can stop here.
Thank you.
Yeah.
Yeah, I think if you also.
Yes, when you talk about FNL here, you're talking about the squeezed modes, right? Did you look into like the geographical or the other FNL shapes?
FNL local, yes,
Yeah.
It is the local, yeah, I don't try to compare with the other.
GML?
No, the GML or regular.
I'm from a totally different field, but for me the FNL it was -4 ±13 is probably not promising, but I don't know how it can.
Yeah, I mean, of course, I mean we are. I mean, from the point of view of LSS, or partial measurement, is not that bad in the sense that until DESI year 1, we were able to see math and error of the order 20 from LSS. I know from the theory point of view that might sound like the error bar is still too high, but this should be improved with new data. So DESI year 3 is coming in, DESI year 5 will come too. So and also Euclid data. So I think at some point we can go beyond the CMB.
Field of view of the data, I mean, the galactic obscuration, or not. I just thinking about the low multiple moment.
Yeah, sure.
And that means that without extra sky coverage in that areas, it will be very hard to improve. What I think of.
Yeah, that is the main issue. You need a very large area, very deep body map, but also understand systems.
Thanks. So for the ARF, you said, I guess, what's nice about that is that it's robust to the systematics if they are not redshift dependent.
Yeah.
But we will have systematics that are redshift dependent. So how robust actually are these results to systematics anyway?
So the issue we have also far with ARF systematics is why is a photometric survey in the end. So the typical photometric redshift error is like 0.06 times 1 plus n, which means you cannot actually measure the or the set. And the ARF is affected by that. But then we would like also to try with spectra from DESI, for example, to understand if, like if we remove completely the Rashi function, we are going to understand.
So one of the techniques you're using is angular redshift fluctuations.
Yeah.
I mean, you didn't go into much detail, obviously, with the time, but as useful as a probe of modified gravity things. So I'm puzzled that you're using it just as a secondary way of getting at non-Gaussianity. And I wonder whether there's a potential for confusion between the two. Could a modified gravity deviation simulate non-Gaussianity as a signal?
You mean if it could be a evolution in
well, I mean, to predict the redshift fluctuations, you need to have the coupling between the density and the gravitational potential. So if that was non-standard, would that look like PNG, even if actually it was Gaussian but non-standard gravity?
Yeah, that's sounds good. I mean, that's something I probably might have to think a little bit more.
Okay, I'd like to speak a little bit.